you collect all the mapping of the readouts to the stabilizer qubit, we call this signature, just telling you which qubit, which stabilizer qubit had which readouts, is the kind of default state, i.e. the logical zero. So you cannot control the readout. It can be 0 or 1. But once you measure the stabilizer qubit, your data qubit is changed into the eigenstate according to that signature, and you just assume that to be 0 logical gate, or the 0 logical qubit, 0 cat. Okay, so just make this a default state. I mean, if you want, you can make it, assume that it's to be 1 cat. I mean, if you make it carefully. So anyway, so that's the initialization step. And the second step is, okay, so you want to do something on the surface code, like putting X gate, logical Z gate, logical Hadamard. But let's say we want to just preserve the quantum information. So you want to see, you want to detect any error occurred in between initialization and the next step. So run the circuit, correcting error here, correcting error. So as I said again, and I may emphasize, we are not correcting error in real life. We are detecting error. And even though I made a correction, it's not really correcting if you really want to put your surface code in a real quantum computer. You just detect, you just write down where the data qubit is supposed to be errored, and then move on without doing anything on actual data qubit. Okay. So anyway, so correcting error is see the measurement, see the syndrome measurement. Or let me write this way. See the symptom. See the symptoms. So which means that the change of the signature after the surface code cycle, or after the syndrome measurement. Okay, so whenever you run the surface code cycle, that ends with the measurement on the stabilizer qubit. So you can call this as a syndrome measurement. So see the symptoms. Symptom is the change. So, and then you want to estimate the um, error configuration for Z errors and X error separately, independently. So if you want to find the estimate of error configuration of Z error, you only go for looking at the X symptom, the symptoms at the X stabilizer, and vice versa. So you can always use, human can do it. It's not a hard question. If it's large surface code, it might take time, but it's not really hard. So you just try to get rid of all the symptoms, and you will be successful at some point. But the question is, we don't go for the random. We go for the best possible probability, which means that which I go for the highest probability, right? So find the best possible configuration of errors by minimum weight perfect matching. And now this is important. So in the last step, we're not really doing something on the data qubit, but it depends on whether you want to simulate a surface code or we really correcting error in the real quantum computer. But at this point, there is no quantum computer has the surface code implemented, so we're just doing the simulation. So for simulating error, um, determine whether the error correction is successful by detecting any chains of error. Okay, so if you have a chain of error, it all not just because it has a chain, there are some other conditions, but let's say in this moment, if you have a chain of error, then it's failed. If you fail at any of these error correction type, any type of errors, then you failed to correct the error. Okay, so here I'm going to explain the part C and D more in depth here. So let's say this is our surface code. So I'm going to draw the picture like this. Let me see. So that's the set error, so rough boundary, so smooth boundary. Okay. So when you look at the, remember the picture right there, we have um, here. So sometimes we have chain of Z like this, chain of Z here, and sometimes we have chain of X right here. Okay. If you see these kind of chains, then it's failed. Why? Um, So we have to think about, we have to talk about the surface nature of the logical qubit in the surface code. So when we make a surface code, when we do the surface code, we assume that the data qubit, the quantum state stored in data qubit is just one big logical state, just one logical qubit, one logical qubit. And we want to do some logical gate applied to this logical qubit. And the only way we can apply it, I mean, one way you can apply it, sorry, is having a chain of Z and chain of X to be served as the logical Z and logical X. So look at, suppose that we have chain of Z like this and chain of X like this. So there is an intersection. There must be intersection, right? Let's say this is our intersection. This is the data qubit. So if you have logical quantum state, let's call it psi bar, and this is a superposition of many, many physical qubits, so it's impossible to write down in complete ket, 0 ket, 1 ket basis. But if I say I apply this Z bar, which is the chain of Z, and this chain of X in this sequence, what if I want to change the order of this logical gate? Logical, and so instead, which means that instead of having Z gate and X gate, let's say I have X gate and Z gate on here. So again, Z gate and X gate, these are logical gates, consist of Z and X gates on these several data qubits, which is physical qubits. The only difference is that, I mean, the only data qubit that shares is one. There's only one data qubit that shares the same position. So the Z gate on the other data qubit can be interchanged. The order can be interchanged, which means that it's commutative because that's just acting on a different data qubit. But on this data qubit right here, if you change, there is a Z gate acting on this data qubit and X gate acting on this data qubit. If you change the order, then it gives you the minus sign. There's only one data qubit doing that, so only one minus sign appears. So because of this identity, these X chain and these Z chain can be served as a logical X and logical Z. So even if you don't have this X bar appeared after the quantum error correction, if you accidentally made this, then we call it failure because of this Z chain, the original quantum state would change its state into different state as a logical quantum state. So we kind of lost the information. We kind of altered the information that we had before. And same thing for here. So if you have any kind of chain that connecting to the left boundary to the right boundary, we kind of assume that if we had a Z logical gate here, then it will serve as an X error, or no, sorry, X gate, logical X gate of the logical qubit stored in this surface code. So we also say this is a failure because it changed the quantum state by as if it's applied by this X gate. Now, how do we find this? How do we correct this? So minimum weight perfect matching. Um, let's say this way. So we have. So let's go for the Z error correction. So let's say we have X and X. Let's say put it X, 3X here. So these three X stabilizer has been turned on. So it has a symptom. So we want to correct error by perfect matching. So what we do is we make a complete graph. Complete graph of, so let's label it here. 1, 2, 3. So 1, 2, 3, complete graph, just a triangle. And but for perfect matching is actually an algorithm that applies to the graph theory. So it has to be graphed. You can consider this as a graph. And the perfect matching only gives you the pairs that completely exhausts all the vertices of the graph. So if you have just 3 edges here, you cannot make a perfect matching. It's impossible, right? If you match these 2 and 3, 1 is left. And in perfect matching, you cannot use one vertex in twice. So 2 cannot be matched with 1 and 3 at the same time. So if you're matched, then it's gone, right? And also in here, let's say, okay, I think that should be chain of Z error that connect these two stabilizers to eliminate the symptom. And how do you get rid of the symptoms of 1 here? We have to go for the boundary, right? Sorry, it has to go up. Let's go up. So there should be something that matching 1 with something else. So that's the auxiliary qubit here, auxiliary qubit. So let's call it 4 here. So it's auxiliary 1. So it's auxiliary qubit, which is closest to the X qubit, X stabilizer qubit 1 here. And if I just have 1, okay, so there is one more possibility of connecting 1 to auxiliary 1 here. So in this case, actually, there is only one way of doing perfect matching, taking this edge and this edge. But that might not be the case. So instead of having this configuration of X error, I could have, let's say, instead of having here, I could have here or here, right? So connecting these two X stabilizer and connecting this X stabilizer to the boundary might give you the lower number of the data qubit that is errored. So in that case, I need the auxiliary qubit that matches with this X stabilizer qubit 2. So I need A2 here. So let's call it 5, the number 5 here. And I can do that. I can have another possibility, right? A3, let's call it number 6. And 2 is connected to A2, 3 is connected to A3, right? So these auxiliaries are only placed here in order to match with these data qubits, or sorry, stabilizer qubit. Only one stabilizer qubits. Okay. And do we need anything else? Do we need anything else here? So let's say I run this my maximum perfect matching, minimum weight perfect matching here. So I need to give a weight. So I need to give a weight for every edge here. So the weight of edge is the number of data qubit connecting two stabilizers. So let's say if I connect 1, 2, 3, there are many ways. There are many ways to connect this, but I want to go for the minimum weight, minimum path, the shortest path. So this weight, let's say W13, is the smallest number of data qubits that connects qubit 1 and 3 in Z chains. So, or in other words, it's the shortest path of Z chain connecting 1 and 3. So vice versa, I mean, for every other edge, you do the same thing. So well, let's say if you want to find weight between 1 and A1, what is it? So A1 is supposed to be the bound auxiliary qubit among all these auxiliary qubit on the top and bottom, which will have the shortest path that connects to 1, right? So just this weight that connects 1 to A1 is the shortest length of the chain that connects that connects the stabilizer qubit 1 to the boundary, the closest boundary. And same thing for the other edges here. Now, is it suffice to have these as a graph to do the perfect matching? So as I said, the perfect matching, uh, once you set up the data graph like this, perfect matching is just graph algorithm. Okay, so let's say let's give a number for this: 1, 2, 3, 1, 2, 3. What is the minimum weight here? What is the minimum weight perfect matching in this case? So I'm not talking about the algorithm. There are many algorithms actually do the finding the minimum weight perfect matching, but let's just doing by our eyeballing here. So we have, let's say I have matched 1 and 3, then I have weight 1, and then 2 is left. But so there is another way of matching these 2 and auxiliary 2. So they're weight 2. So the total weight is 3, right? So I only need 3 data qubits to connect these stabilizer qubit, which means that get rid of all the symptoms. What are the other ways? If I match these two, then I have weight 2, and I need to connect these 3 and auxiliary 3. So the weight sum is 5. So it's bigger actually. So don't go for this. And how about these two? That's weight 3 and 1 auxiliary 1 have a weight 1. So some weight is 4. So actually still big. So I think the best possible, lowest minimum weight perfect matching is when I do this. Okay? But again, okay, so if you just see this problem graph theoretically, the perfect matching is not possible because if I do this, go for the minimum, there's no way I can match A1 and A3, right? So I know that this should be the answer for our surface code, but in graph theoretically, this is not the right way of doing perfect matching because I cannot match A1 and A3. So we need more edges here with a 0 weight. Because we don't want to add more weights because there's no data qubit that connects A1 and A3. And we don't need to actually connect A1 and A3. It's only for securing our minimum weight that is already found. So in this case, then A1, A3 they can be connected by this edge with a weight 0. So the weight 3 is preserved. So we only need 3 data qubits to make a perfect, to get rid of the symptoms on these stabilizer qubits. So this is the basic tree configuration. There is a way to make it a little bit simpler, but basically, if you have more stabilizer, then you get the two complete graphs together, and then they are matched with edges, and all the edges on between auxiliary qubit has to be set as 0, and the weights of other edges are set as the shortest path between these edges, between these stabilizers. It makes sense? So once you find this, this only gives you the path. I mean, only gives you the matching, right? So, but here, you really want the path, right? So I only have a matching. Let's see. Mm, okay, so how about this one? So, how about, let's see. Um, so I want to. So let's suppose that we have a symptom on here and here diagonally. So I know that the weight is always 2 because there's 2 data qubits, which are the shortest or smallest number that connects these two. But and suppose that we get these two pairs after the perfect matching. But now we have to choose which path that actually occurred to connect these two stabilizer. Is it here, this path or this chain or this chain? We have to decide. But there's no priority here because we assume that every data qubit has the same rate, the same chance of error. So just random. You either go this way or that way. It doesn't matter. As long as it's minimum, then we go for it. So, so perfect matching only gives you the matching pairs. Finding the path is different story. And here's one more question. So there are 3 types of cases that consider to be error has corrected. So one is you have loop. Loop of X or loop of Z, doesn't matter. Loop, then it's not failure. Okay, and if you have a half loop, so in this case, if you have a Z chain of half loop either on the top and bottom, then it's not a failure. Another case is that if you have chain of Z of even number of chain of Z connecting to one boundary to opposite boundary, it's not a failure. So it's even number. So why is that? First of all, think about this case. Why so it's not failure. So successful, that means it's successful. It's successful means that we don't change our logical quantum state by applying this loop of Z errors. Why is that? So we assume that the logical state is the eigenstate preserved by these all measurement qubits. And if you have this data qubit, if you have this loop of Zs, then what kind of X logical X is applied here? What kind of X logical X applied? We always have 2 or even number of data qubit connect intersecting with these X chains, right? So whenever you have an even number of qubits intersecting each other, so only thing that we require to be the X gate and Z gate as a logical gate is whether it changes the sign or not when you interchange the order of application of X bar and Z bar here. So because of this even number of data qubits, if you interchange it, the sign changes in even numbers, so it's always the same. So it's considered to be the same logical state. And same thing for here. If you have a loop, then it passes the even number of data qubits whenever you have an X chain. So it's also preserved as the original state. And how about this? So you can think of this as a big loop or kind of a half loop, half loop, two half loop. in half loop, taking the same, sharing the same boundary here, or yeah, or you can think about this as a big one loop here. So same reason. So whenever you have chain of X here, it always intersect with and at the even number of data qubits, so it does not changes the sign. So when we say this, I'm saying that Z bar is the Z, it consists of all the Z gates on all the data qubits, Z gates on all the data qubits on these yellow lines here. And not just one. I'm not saying that these two are separate the chains. So the Z bar is consistent of all the Z gates on these two lines. And same, so in this case, I'm thinking about this separately, but in this case, I'm taking as the same one thing here. So these are three cases that we consider that our error correction has been successful. Um, Let me finish the one quick remark. So I made this path just to make this visualization. So just give you how it actually correct error or not correcting the error. But if you really want the simulation, I mean result, whether if you just want the success or failure of your simulation or error correction, then you don't need to draw the path. All you need to do is what? Whether these occurred or not, right? So symptom will change. Symptom will disappear, whether or not you successfully corrected the error or not. So these results, there are common property of these results. So this one have no Z chain or Z error or Z gate on the boundary qubit on top and bottom. So the sum of number of Z gates remaining on the boundary qubit is 0. How about here? So there are two data qubits, which has Z gate applied, and here too. So there are even number of Z gate remaining on the boundary qubit. And here also you get 2. So whenever you have even number of data qubits on the boundary, which still has the Z gates, then it's successful because it's always has to be one of these cases. So you don't even need to count the or think about the possible path of these chains. Just count the number of Z errors on this boundary, remaining on the boundary, and check the parity, whether it's even or odd. And that gives you success and failure result. Okay, that's in the beginning of the class, I was intended to give a more detail about the algorithm, minimum weight perfect matching algorithm. It's quite interesting, but not really connected to our quantum computing. So I might skip this part. So in the next time, I'm going to talk about I talk more about the other logical gates,